Good afternoon again. We're going to assemble the reflux system first. In your lab manual, if you have the ebook, not sure the page numbers, how it goes, but for the other book is page 126, the equipment that we need to assemble the reflux system. So we are using the hot plate today, not for heating up the sample, but we are using the hot plate to make sure that we can stir the reaction mixture. When you are assembling the reflux, you want to make sure that to get the hardware first. So for the hardware, we do need clamp to hold the. We need a clamp to hold the condenser, to secure the condenser, and for that the best clamp is the 3-finger clamp. With the 3-finger clamp you can rotate, change the arm side, and you can change the angle for better fit, because your condenser needs to stay straight. You should always have a utility clamp using to secure the boiling flask. I believe it's 2 grams. 3 grams actually. Yes. So this needs to be centered, so I'm going to rotate it around. Otherwise the stir may not work perfectly or properly, at least. We have to make sure that this is for the condenser. Why do I have to bring the hardwares out first? Because I don't want to have too many glasswares while I'm setting up the hardware in case of any incident, any accident. If I drop anything, I do not want to get lab breakage. Try to minimize the lab breakage. When you are dealing with glass joints, you should always have your glass joints greased using vacuum grease. So you want to make sure that the glass joints are greased, because if it's not greased as a result of heating, it's going to freeze up the pieces of glass together and you won't be able to separate them. The blue clamps that I have, you have the blue clamp somewhere? I don't know what they are. I have one. Okay. Okay. So we need the. I have all the equipment here. Since I have all my equipment except the condenser connected, I'm going to add the chemical. So if I connect it, then I don't have to take it out. Going to add following the procedure. So we are going to follow the procedure to get the. To bring my own glasses. 50 milliliters of water. So we measure 50 milliliters of water. And when we are adding liquids, especially to boiling flask, I prefer the boiling flask is not any electronics, so we don't spill any of the water on the electronics and any of the chemicals. And 3 grams of potassium permanganate. I'm going to add 1 milliliter of the chlorotoluene. So the chlorotoluene is kept inside the fume hood. I'm going to just take the flask to the fume hood to add the 1 milliliter, and I bring it right back. Okay. So when you follow the procedure, you just want to make sure that everything is asked in the order is asked to add those chemicals, and you want to add sodium hydroxide. You're going to add 3 pellets of sodium hydroxide. Okay. The boiling chips, since we are using a magnetic stirrer to stir, that could also act as a boiling chips. But if you don't have the magnetic stirrer, or anytime you are doing reflux or distillation, you want to make sure to add the boiling chips. Okay, now we're going to assemble and finish up assembling the reflux. Whether it fits. And we are going to turn on the power regulator, turn on the stirrer, make sure that it is stirring, mixing the solution. And I'm going to adjust it for now at 60 while it is warming up. I finish up the assembly. To assemble the water hoses, to attach the water hoses, I need to attach the 2 water hoses. One, water coming in. The lower end, water coming in. And the upper end, water going out. So this side of the hose is going to be going down the drain. Going to open the water very gently, very slowly, because if you open it with high pressure, it can cause water splashes, and we don't want any water splashes at this point. For electronics. this for 45 minutes minimum to make sure that the reaction is complete. Okay. Okay, so while we're waiting for that, we can go ahead and talk about the theory of the experiment and answer your questions to make sure that you have a clear idea or better idea of why we are doing this experiment, how we are doing, what's the purpose of the experiment. So I'm going to move this to a place of the lab that there is no chemicals. This point, so I can take my glasses off because I didn't bring my other glasses and these are not helping me. The temperature that I adjusted at 65 now, it might need adjustment to lower it. There is a problem with this reflux. Then now you could see the ceiling here with the brown spots in the ceilings. Those are coming from this experiment. Do you see those brown spots in the ceiling next to the light? If you see them, that is the permanganate shooting to the ceiling. So we try to avoid any of those accidents. So we use the stirring rod to stir it constantly to break down the bubbles so it doesn't shoot out. And so we lower the temperature. So when we are sure that the solution has started boiling, we are just going to lower the heat, maybe 35, 40. Gentle is good in organic reactions for reflux, for distillation. Gentle boiling is good, and then gentle flow of water. Both of them has to be gentle, and we are just using the common sense. Sometimes you do everything possible, still you have accidents, but at least we know that if the temperature is high, we're going to have accidents, and if the water is open with high pressure, it's going to cause water splashes because those water hoses are not very tight. So, and it can't be that tight. So we just lower the flow of the water to gentle flow to make sure that is not causing any problem. So now that we have time, you could all use your mics, and if you want to use your video, it's fine. Actually, maybe just the mic because it's recording and we are saving for later. I want to use the videos at least to get to see you, but probably after I stop recording, then I would do that. When we are doing the data analysis after the experiment, we can do that. So,
Professor?
Yes.
Few questions in the chat. Just going to scroll up and read them real fast. What is the compound number we're using? The unknown? Unknown, like 1, 2, or 3?
The unknown B. We are using unknown B.
Thank you.
I don't know what it is yet, but we are using unknown B. B,
Bravo,
like a boy.
right? Bravo, thank you.
Yes, B like a boy or Bravo, yes.
And you said that the temperature is set at 65 C and its power regulator 60%, you said?
65%. The power regulator is used at 65%, and I'm going to watch it and monitor it. I would never suggest anybody to stay close to the setup, even though we do everything. We do have those shooting of the chemicals out of this particular experiment somehow. So we try to keep it low. And at the beginning, we start with 65, and then we lower it. We lower to 35, maybe maximum 40. Okay. Can you tell me what's the purpose of the experiment? Abigail, if you can use your mic and tell me what's the purpose of the experiment? Carissa?
Hello?
Yes, Abigail.
So is it to identify the unknown chlorotoluene?
To identify the unknown of chlorotoluene, what are the possible known samples? So your unknown could be what? What could be your unknown? Jessica? Dominique? Who's answering? Anyone?
2, 3, or 4 chlorotoluene.
Was that Justin or Louis?
It was Lewis.
Louis. Okay, it could be 2-chloro, 3-chloro, or 4-chlorotoluene. And we cannot use the boiling point because on page 125 of the lab manual, if you look at the boiling point for those compounds, boiling point for the 2-chlorotoluene is 157 to 159, and then 3-chlorotoluene is 160 to 162, 4-chlorotoluene 162 to 164, too close to identify your unknown based on the boiling point. So in this experiment, we are going to oxidize the toluene. Toluene
Wow.
is a benzene ring with a CH3 group attached to it. So it's an alkyl chain on the aromatic ring. If you oxidize toluene, it's going to change to benzoic acid. So you could get 2-chlorobenzoic acid, 3-chlorobenzoic acid, or 4-chlorobenzoic acid. And as a result, look at the melting point. When you look at the melting point of those compounds are far apart from each other. And when you measure the melting point, you can identify your, map it back to original compound and identify your unknown.
Professor, can you please say those boiling and melting points again? Because I'm missing that page in my lab manual. That makes things awkward.
That's not possible. It's not possible. If there's a table right after the chemical reaction, look through your lab manual, please. There's a general reaction, page 3 of the experiment 12.
Oh no, it's just in
Page
a wrong
135.
order. Okay.
Did you find it?
Yes, it's just in the incorrect order.
Yes. Did you find the?
Yes, it's just in the incorrect order. It's like 2 pages later, so that's no big deal.
Okay, perfect. As long as you find it, that's fine. Then there's it comes in like a table format, so compares the boiling point with the melting point. Now the melting points are far apart, and you can identify. When you are identifying this compound, let's say you have you find the melting point to be 190. What would be your unknown? I think that's also a question on the pre-lab.
3-chlorobenzoic acid.
Yeah,
And
it's
how
likely
do you
3-chloro.
justify it? 3-chloro? Did you say 3-chloro?
Yes.
Okay, for 190?
Yes.
Okay, anyone else?
4-chloro.
And how do you justify it?
Well, because if you have impurities in your sample, that's basically can lower the melting point of the actual compound. And the starting melting point will be too high for it to be any other benzoic acid.
Okay, very good. The melting point depression It's the idea of if you have your compound is 100% pure, is going to show the melting point that is in the you find in literature value, and that would be the melting point of 138 to 140 for 2-chlorobenzoic acid, and 3-chlorobenzoic acid is going to be 155 to 157. That is for pure dry sample. Now, if your sample is not pure, the melting point would never go higher than what the literature value is. So you should always keep in mind what you learned. Colligative properties is a boiling point elevation and freezing point depression. So freezing point is always depressed by impurity if you add something. So if you have 190, that is not possible for it to be 155 or 138 corresponding for 2-chloro or 3-chloro. And how do you justify that 190? When you just justify it based on impurities, you would say your sample is not pure or it wasn't dry. Sometimes you purify your sample properly, but if you don't actually let it stay in the oven for long enough, if it doesn't dry, then the water or the solvent that you wash your product with is going to act as impurity. Very good. There was a video for reflux, video for assembly of the reflux. There's explanation for why we are using reflux in the lab manual as well. Michael, if you could turn on your mic, and can you tell me under what condition should we use reflux? If chat is easier for you, then when I open the chat, then I won't be able to see your name, so I won't be able to call on you. So Tanisha, Noor, Michael, any of you can turn on the mic quickly. Tell me what is the, yes.
I think when we use when we want a controlled environment, then we use the reflux.
Controlled environment. What do you mean controlled environment?
Like a consistent temperature.
Consistent room temperature, consistent high temperature.
Consistent high temperature.
When you have a reaction that it takes 1 hour, if you perform that experiment in an open container, let's say you mix the chemicals that we just mixed and you place in a beaker and you heat it up for 1 hour, when it starts boiling, because it has to boil for 1 hour or 45 minutes, the sample is going to the solvent is going to evaporate, and you have to refill the solvent constantly. The problem with water is minimal because it's water vapor, even though it might take and kind of just like a steam distillation, that it takes the chemicals with it. When it changes to steam, it can evaporate the main ingredient as well. So it's going to be loss of reactant, and at the same time refilling the solvent. And if your solvent is ether, if it's acetone, if it's any other alcohol, or solvent is hexane, you don't want the vapor of that in the lab. It's not safe to have vapor of those chemicals in the lab. So to avoid health risk and loss of chemicals and loss of reactant, whenever you are looking for a high temperature, consistent high temperature for a long time, the best solution is to use reflux. So when the reflux is taking place, I'm going to take the video now to the system. Let's just put my safety glasses back on and get close to the setup. Okay. Do you see the setup?
Yes.
Yes. Okay. You see the water is boiling. I'm going to, the solution is boiling. And as the solution is boiling, the vapor goes up it condenses and it comes down. You see the droplets going down the solution? That is called reflux. It goes up, it condenses, and it comes back to the boiling flask. So when we say reflux, it's like a returning, like it's used as an acid reflux, but it's different. Acid reflux, it works opposite. This one goes up, and then it comes back. So you see how the reflux is actually taking place here. Vapor going up, the condenser, water condenser that we have here, it cools down the vapor, it changes back to liquid, and then it goes down to the reaction mixture. And I lowered this setting now to 30 to make sure that we are not getting splashes to the roof like we had in the past. And the stirrer is also spinning, and hopefully it breaks the big bubbles to small bubbles so it doesn't explode or it doesn't splash out of the container. Okay. Okay, what is the purpose of using permanganate in this reaction? Now, anyone with the mic handy, we can answer the question.
Hello?
Permanganate. What's the purpose of using permanganate? Dominic?
Permanganate would act as an oxidizing agent for the chlorotoluene.
Permanganate would oxidize the chlorotoluene to chlorobenzoic benzoic acid. Which one is the limiting reactant? The permanganate or chlorotoluene in this case?
In this case, it would be the chlorotoluene because we have a step. Because we have a step to eliminate excess permanganate later on.
Very good, because if you calculate the mole ratio based on the grams of permanganate, and you have to convert the 1 milliliter of chlorotoluene to mass of chlorotoluene and calculate the mole for chlorotoluene and calculate the mole for permanganate. You compare the mole ratio. You find out that permanganate is going to be excess compound based on the number of moles. At the same time, if you read the procedure carefully, all the steps, one of the steps, it says that you are going to remove the excess of permanganate. So what is used to remove the excess of permanganate?
Sodium bisulfite.
Sodium bisulfite. If you use sodium bisulfite, how do we know we have removed the permanganate? Or so, in other words, how much of sodium bisulfite should we use?
You start with 5 grams or 5 milliliters at a time
Until
the purple color is gone.
Until the purple color is gone. When we are doing actually oxidation reduction reaction, the chlorotoluene is being oxidized, the permanganate is being reduced. So permanganate from KMnO4 is reduced to MnO2, manganese dioxide, which is a brown color precipitate, and the permanganate is a soluble purple color solution. So when it's reduced to manganese dioxide, the purple color is going to go away. You are going to use 5 milliliters at a time of the reducing agent to reduce the permanganate other than the chlorotoluene. So you are using sodium disulfide to reduce the excess of permanganate. And when the color disappears, you are sure that you have used enough of the sodium bisulfite solution. There was a question in the pre-lab, what is happening to the pH of the solution as the reaction progresses?
The pH
So
goes
actually-
down.
And what causing the pH to be lowered?
Hydrochloric acid.
We're talking about while the reflux is taking place. At the end, yes, that's a different procedure, like different step of the procedure. But while the reflux is taking place, what is happening to the pH? pH decreases
because acidic
Danielle?
hydrogen.
because
The hydrogen on the benzoic acids as they're being formed
hydrogen
are more
and
acidic.
benzoic acid. Okay, so sodium hydroxide that we use, the 3 pellets of sodium hydroxide, it made initial solution, basic solution, and as you produce benzoic acid, sodium hydroxide is being consumed and is also being neutralized with the benzoic acid that is being produced. So since it's being neutralized, the pH is going to be lowered because we started with high pH. Very good, very good. So some of you are answering these questions with the chat, which is okay. Good sodium bisulfite. So I just want to make sure that I have them in record. Very good. The filter paper. We are using the 42 number, paper number 42. The Wattman paper, filter paper of 42. This is just to make sure that the openings of the filter is small enough that will catch all the particles of manganese dioxide, because manganese dioxide is a brown color. Your final product is supposed to be white color, white precipitate or white crystals. So we don't want to get the brown color mixed with that, as the impurity is going to change the boiling point, the melting point, and it also changes the color of the product. The reaction, when you are using potassium permanganate, you know from general chemistry that permanganate is a oxidizing agent, and potassium permanganate with heat, it can work in basic solution, it can work in acidic solution. To design this experiment, I picked purposely basic solution. I did not want to use acidic solution for this reaction. Can anyone tell me what would be problem experimentally if we use the acidic permanganate for this oxidation reaction? It does require like a little bit more thinking, so take your time. One of the questions, I believe there's a question in the pre-lab, and if not, it would be a question in your exam, is a hint for you to answer that question, actually. Question number 4 on the pre-lab.
Can you repeat the question?
Yes, permanganate can be used in acidic solution or basic solution as a strong oxidizing agent. For design of this experiment, I chose the basic solution rather than acidic solution. Could you tell me what would be problem if I use the acidic solution?
Would
Wouldn't
it be
it be-
because in an acidic solution it would extract the benzylic hydrogen and not allow for oxidation to take place first? So the acid-base reaction would occur first, then the oxidation reaction, since the acid would extract the benzylic hydrogen for the initial chlorotoluene.
So you're saying chlorination would take place?
No, the initial, if you react the permanganate in an acidic solution, would the acidic solution react first and extract the benzylic hydrogen of the chlorotoluene before it could be oxidized to a benzoic acid? So basically, would the acid-base reaction occur first and an oxidation reaction?
For the benzylic hydrogen, it would require a chlorine to be replaced, right? Not chloride.
Oh, like a conjugate base?
Yes. It would require chlorine or bromine or NBS, like bromo-6-enamide or something of that nature for the substitution type reaction.
Would it be difficult to take out
What-
the excess permanganate?
The excess permanganate. Okay. Anybody else? So I'm not saying any of the answer is incorrect. I just want more responses, and I want to make sure that all of you can participate, and then we summarize all the answers. So what else could be a problem? If your reaction mixture, actual reaction takes place in acidic solution rather than the basic solution. Okay, that question 4, it did not ring any bell. Your product in the reaction mixture, you're not actually getting benzoic acid. You realize that, right? Because you have sodium hydroxide, benzoic acid would react with the sodium hydroxide that's being produced, and it changes to sodium benzoate. So it changes to sodium benzoate. Sodium benzoate is a highly soluble compound, and in basic solution, it will stay soluble in the solution. So it stays in the solution. So when you are filtering away that manganese dioxide, the filtrate that is coming out actually is going to contain your product, because your product was highly soluble in the liquid portion or in the water or in the basic solution, a basic aqueous solution, and it's now in the form of the solution is going to be extracted or filtered out. So you will see the filtrate. If it's acid, if it's an acidic, if the oxidation takes place in acidic solution, the benzoic acid is going to stay in benzoic acid form. So the hydrogen is going to stay attached to benzoate. So you actually have benzoic acid. You have probably used benzoic acid for recrystallization for your organic one, or anytime for also for extraction, because it's a good compound, and the solvent is just hot water, because it's going to crystallize in cold water, or if you lower the temperature goes below like 80 degrees, it's going to crystallize. So if it's acidic solution, you have the mud that is mixture of manganese dioxide plus your benzoic acid, crystals of benzoic acid. At any temperature below like 90 degrees, you would have the mixture of the two. So when you filter it, you're not going to get the product. You're just filtering the water out. So it would make it impossible to filter the product. Does it make sense? Yes? Okay. So if it's acidic solution, let's say in the boiling flask, you have HCl mixed with your permanganate. Your toluene is going to change to benzoic acid, but that benzoic acid is going to be crystallized. As soon as the temperature it's lowered slightly, is going to be crystallized. And definitely during the filtration, it would be in solid form. And if it's benzoic acid powder, you cannot separate the manganese dioxide from that. So you have to first separate it in the liquid format, in aqueous solution format, and then you add your HCl to acidify the solution to change the benzoate or the sodium benzoate back to benzoic acid, and your benzoic acid is going to be now crystals that you can filter it with the vacuum filtration, and then you separate. Does it work or no? Does it make sense? So under acidic condition, you would form a solid product before the filtration step. Yes, that's great. Yes. Yeah. So under acidic condition, you would form a solid product, premature crystallization basically. A solid product will form before the filtration step, and you will not be able to separate your product because it's a mixture of two solids. It would form a mud, a mixture of two solids and solvents. Okay. Do you have any questions? Any questions from the pre-lab that you had difficult time to answer it, or any questions from the procedure why we are doing any of the steps?
Yes, Professor.
Sure.
What does 42 mean in filter paper? In the filter paper.
42 filter paper.
Okay, so Abraham and Tikva were saying that it's just a gauge, which is what I was
Four
guessing,
size.
but I wasn't 100% sure on that.
Okay. So I brought the filter paper. I went to bring the filter paper to show you. It might be very hard to feel it or to see it because the thickness of the filter paper is different if you are using a P8 paper or you are using the filter paper 42. 42, it's much thicker. It's like 2-3 times thicker than the P8. And the reason we are using this because of the pore size is smaller, and it does not it doesn't allow any of the manganese dioxide to pass through the openings. So what happened with the Google?
That's what it told me. I just wanted to make sure from you.
Okay. Any other questions? Not yet? Okay. Any questions from earlier? You said you want me to open the pre-lab so you can see the answers or what you did wrong. Can you just look through the questions since you have the questions in your manual and tell me, was there any of the questions that was not easy for you? So is there any questions that you were not sure about your answer? So I can help you with the answer now. Which questions? Okay. I did answer some of them, and I just want to make sure that everyone is fine with that. My only question was about the filter paper, but I understand it now. Perfect. Very good.
I have one question.
Sure. What's your question, Louis?
Um,
Was it Louis or Justin? I don't know.
how after
Yes. What is your question?
to how long after lab?
Something wrong with the.
How long after the lab is it posted?
Can you please type your question? I'm sorry, because the mic, I think it didn't work. How long after the lab? Oh, lab is this posted for future reference? Next day, or as soon as I get a chance. I won't be able to post it before like 3:20 because I set up the time until 3:20, and then I am going to as soon as I get a chance, I would give you the link for this lab as well. You had a question about how would you know the pH is going down, or what causes the pH going down. pH for base is higher than 7, and therefore acid is lower than 7. Chlorotoluene is not acid, but when chlorotoluene reacts with permanganate, is going to change to benzoic acid, which is the acidic compound. Now that acid is going to react with base because it's going to change to sodium benzoate actually, and with the sodium benzoate is going to lower the pH because now it's consuming the sodium hydroxide during the reaction. So if you consume sodium hydroxide, that means it's neutralizing the base. And if you neutralize the base, the pH is going to go lower than what it was before, but still is going to be higher than 7 because your solution still is basic. It's just that the pH maybe from 11 it goes to 10, and based on the number of the sodium hydroxide pellet that we add based on the procedure, 2 to 3 pellet, that's more than enough to keep the solution basic, even if you produce 1 gram of benzoic acid. Perfect. Very good.
Professor, I had a quick question.
Sure.
You said that the solution is considered basic. At what point does it become at what point is it considered acidic? What is the change that happens? And then my other question is, okay, and just one other question really quick. My other question is, you said that chlorotoluene reacts with permanganate, which changes into, and I didn't catch the rest of what you said.
Yes, it changes to benzoic acid, chlorobenzoic acid. It would change to chlorobenzoic acid. That is the reaction you have. I'm sure you have that in the reaction or general reaction that you wrote down. That's on page 125. The CH3 is changing to COOH. CH3 with the benzene ring is the toluene. COOH is the benzoic acid. And the chloro is going to be somewhere there based on your unknown.
Okay, perfect. And then for my other question about when it becomes acidic, when the solution becomes
when would
acidic.
it become acidic? So before the filtration, we want to make sure our solution is basic. That's why we are adding those sodium hydroxide in there. After we do the filtration, we get a clear liquid, and that clear liquid contains the sodium benzoate or our product, but in solution. When we add the HCl, we add enough HCl to make sure the solution is acidic. We can check that with the pH paper, and I think we have the pH paper here. And we check with the pH paper to make sure is pH paper changes color to red, that is pH is low enough. Or when you see that precipitate is coming out of the solution, that means the solution is basic. Now, with the solution being, I'm sorry, the solution is being acidic. In acidic solution, this is like selective precipitation also from your 1046, if you remember anything from 1046 at this point after passing organic 1. So it's selective precipitation. So you change the pH to precipitate the compound. You change the pH to make it dissolve. So benzoic acid in high pH or in basic solution is liquid, is soluble. It changes to a soluble compound, but in low pH after adding HCl, it precipitates because now HCl reacts with the sodium hydroxide. It removes all the sodium from the sodium benzoate, and then you get benzoic acid, which is solid at room temperature. So after the filtration, we add HCl purposely to make it acidic, because we want to precipitate. And after we change it to acid, to acidic solution, we also place in ice. Did you watch the video about precipitation, like at low temperature? I posted the video. I don't know for this experiment or the next experiment.
Yeah, versus the crystallization, where one's more impure, or crystallization is a more pure technique than just simply precipitating, because that leads to impure.
Yes, crystallization. When you are doing crystallization or recrystallization of your compound, you want to make sure to lower the temperature, because solubility is directly related to temperature. The higher the temperature of the solvent, more of your product is going to be dissolved in the solvent. So when you lower the temperature, you make sure the solubility is less. So most of your compound, it comes out of the solution and precipitates out or crystallizes out of the solution. And if it does crystallize out of the solution, then you get better percent yield for your product. New question, will we be weighing the filter paper soon? Also, do we use the melt temp to find the melting range of our unknown? Yes. Today's lab and next lab, we have 2 labs that are long, so it's a good start. So we expect to have that. Excuse me, can we get that charger? Things in the bag. Just pull the bag to me. Just pull it. Didn't realize. Okay. I am sorry.
Welcome back.
Yes, I'm back. So we are missing one student. Okay, I was getting ready to take attendance actually. Okay, do you have any questions for me? What did I answer the last question you had? Okay, looking for your questions.
I'll scroll up for it.
No, thank you.
Huh.
Okay, because when I go back, then I don't get to see the chat because it,
Okay, she was asking, will we be weighing the filter paper soon? Also, do we use a mel temp to find the melting range of our unknown?
yes we are, yes we are, but we have to get the product first. So we just turned on the oven for faster drying of the product, and we are. Did you keep track of the time? Do you know if it's 45 minutes or not since I started the reflux? Yes, it's 45 minutes. Okay, so it's good discussions. If it's over, then we are ready. I also see that the bottle, the boiling flask is brown color, and with the brown color, that means most of the permanganate has been reduced, so the reaction looks like complete. So we can go ahead and do the second part of the reaction. So a good practice is that while the reflux is going on, I did the setup for 100 degrees Celsius for water for the oven because the solvent that we are using for this reaction or washing or precipitate is water. And if I look at this table for melting point, the melting point is 138 to 140. That's the lowest melting point we could get. So I'm sure if I put at 100, I'm not going to melt the compound in the oven. Hopefully, it's pure enough that it's going to melt higher than 100 degrees Celsius. If it's if the oven needs to be always set, so I'm giving you all the explanation why we do this, so it makes sense. So it's not just a number. The oven needs to be set higher than boiling point for your solvent, but it has to be lower than the melting point of your compound. So if you want to design experiment, you have to carefully design it in a way that you use proper solvent, so your solvent actually evaporates less at the lower temperature than the melting point of your compound. Otherwise, while you're trying to evaporate the solvent, your compound is going to melt inside the oven, and then you take it out, you don't have your compound. So I'm going to set up. Can you tell me what's the next step? So I quickly set up what you need. Your next step is filtration, right?
Yes.
Boiling point of the solvent, yes, but lower than melting point of your product. Exactly. Okay. Let me set up the gravity filtration.
Well, since she said that the permanganate is all brown, then there's no permanganate left. It's boiled off, so she doesn't need to test for it.
Good. I'm still going to check it. I'm still going to check it to make sure that there is no permanganate left. But to stop the reaction, the first thing I would do is I'm going to turn off the heat. I turn off the heat first, unplug the electronics. I don't want any electronics to be on. Then I'm going to, that's how I stop the heat first, and then I stop the water. So I'm going to remove this, bring it higher. Usually you work in group of 2 people, so it makes it easier. Actually, there is some permanganate left, but since it's been 45 minutes and we do have excess of permanganate, it's okay to stop the reflux at this point. Going to remove the heat, let it cool slightly. The flask is really hot, and for me, I rather to open the clamp, the utility clamp, than opening the flask. Because if I open the utility clamp here, I can use the utility clamp as a handle or a holder for me. And of course, this should not be placed on the bench top. So we take a donut and we place it in a donut if you want to keep it. So at this point, I'm going to take it to either take it to fume hood, but then you won't see it. So I'm going to bring the sodium bisulfite here to add to my reaction mixer so you can see it. Okay, if you can see me, I'm going to measure 5 milliliters of sodium bisulfite, sorry, and place it or add it into the reaction mixture. The procedure, it tells you to check with the dropper, take a drop and check it on the filter paper. I normally don't do that. I first check for the shade of purple color. If it still looks some, shade of purple color to me, to my eyes, then I can trust it and say it looks like it needs more of sodium bisulfite. So I will add more of sodium bisulfite. Okay. Now, no shade of purple color here. And now it's safe for me to go ahead and do the filtration. So in order to do filtration, I set up my filter paper. For gravity filtration, we are using the glass funnel. We are using the 42 paper, folded in half, folded one more time in half. Place it inside the glass funnel and add a few drops of water to make sure that it stays. It doesn't move. Sorry, I don't like that to be up high and I couldn't bring it down. So I have to use a different setup. The tip of the funnel, the end of the funnel should be slightly into the beaker because it is much higher. If it slightly move out, then you could see the splash of the chemical everywhere. But if it's into the beaker, even if it moves, it will stop by the beaker. So it's kind of, it gives you warning. Be careful, you don't want to splash your chemical out. Okay. This is going to take a while because filtration is not fast. And it makes sense based on the filter paper that we are using. For practical purposes, and just to see how you are doing this test, I see that there is no purple color, but to test it, you are going to use a disposable pipette. Take a drop of the liquid or the mixture, place it on the filter paper. You place it on filter paper and you look at the color around that spot. If is white or no purple color, then you are good to go. That's why I started the filtration, or that's when you start the filtration. A clear liquid is being recovered. So while I'm waiting for this filtration, a good practice for any chemistry student is to get the equipment and chemicals ready for the next step. Could you tell me what are the chemicals that I need for the next step? So I make it happen to make it faster, or at least get ready.
You'll need 5 milliliters of hydrochloric acid,
Hydrochloric acid. Okay.
5 milliliters,
Uh-huh.
and then you will also need some litmus paper or pH paper.
pH paper or litmus paper. Hydrochloric acid. So I'm going to get the hydrochloric acid to workstation. Okay. I have the hydrochloric acid. I have pH paper. Can you tell me what's going to happen if I put the hydrochloric acid in the beaker now? What would happen? Sodium bisulfite, about 10 milliliters, but the quantity is really not important. Yes. Okay. That's. Do you think something would happen terribly wrong if I put the acid in the beaker? This is just the top. It's not like.
It should, I mean,
It
as you
should
as it drips
just
down, it'll
it, right?
yes.
Someone is asking how did we test for permanganate to make sure it's gone? I guess your video was off for. This is how we tested for permanganate. We put a drop on filter paper, and if there is no purple shade on the side, on the around it, it means it's gone. Yes, you look at the color of the the ring around the precipitate and the filtrate. Well, I have never done this before, but I'm going to try it for the first time to see what happens. I'm going to place this in ice. I'm going to place it in ice and add the acid.
Right now, is that the vacuum filtration, or is that what kind of filtration is that?
This is gravity filtration.
Okay.
Is a good question. When do you use gravity filtration versus vacuum filtration? You know that?
I think in one situation you need to rinse it.
No. It's sure we are using the vacuum filtration later on, but under what condition you would use vacuum filtration? Under what condition you would use gravity filtration?
Whenever we use gravity
Gravity is
filtration, we're
liquid.
going
Again, sorry.
Gravity is liquid and solid is vacuum.
Okay, it looks like you've read it, but I want to make sure that it's clear, your answer. Can you elaborate? What do you mean by gravity is liquid?
The vacuum would help to properly take out the liquid and properly separate it from the
Yes.
precipitate, and gravity is just liquid, so you don't really need much force to separate it.
Uh-huh. When you are dealing with when you want to keep the liquid portion, filtration is to separate solid from liquid. When you want to keep the liquid portion, you want to use gravity filtration because you don't want any of the solid to be forced out of the filter. So you are not applying any vacuum. So when you are keeping the liquid portion only, gentle filtration, gravity filtration is sufficient. As much liquid that comes out based on the weight or the gravity, we should just leave it at that. When you are trying to keep the solid, you don't want any liquid to be left in the solid, so you apply vacuum. When you apply vacuum, it applies suction or strong vacuum. I hope the vacuum is on. No, it's not on. The vacuum is not on, but hopefully I have a pump that it should work. So we use the pump to create the vacuum, and then the vacuum is going to pull all the solid out. And when it pulls all the solid out, it makes the sample to dry faster. So we don't want any solvent to remain mixed with the. If you could see there, it's turning cloudy. And this cloudy means that precipitate is forming. And I am glad that I put in ice first before I put the acid because it's out of the fume hood. Normally, we place that in the fume, we add the acid in the fume hood. But now, since the solution was cold already in the ice, when I add the acid, it didn't cause any fume coming out, which is good. And we have the solid formed already in the beaker. We have more additional liquid that is joining, but at least it gives the solid to settle, and the filtration is going to be faster later. Okay, when you try to detach the water hoses, just going from one side to the other, first of all, you turn off the water and don't detach the top portion. First, you detach the bottom from the faucet. You let the water drain completely. When the condenser is empty, because you detach the bottom portion, then you can get the hoses, disconnect the hoses from the top and bottom. Of the magnet. Okay. While I'm waiting for gravity filtration, I'm going to assemble the vacuum filtration. Here is the vacuum filtration. A Buchner funnel, a vacuum flask, and this one is actually a trap. Why do we use a trap? Because we don't want any of the liquid from the Buchner funnel goes into the pump. The main vacuum valves that we have here, they actually have to turn on the whole system, but they shut down because of the closure of the college. So I have the little pump, vacuum pump that I'm going to bring in. So we don't want any water splashes or liquid splashing into the pump. So we put a trap to make sure that any liquid that it goes back, it stays in there. Electronic don't like water, I guess. That's one. So we have a little pump that creates vacuum. Make sure it's working. So basically air is being pulled in from one side, which creates the vacuum, and comes out from the other side. Just have to test and attach to the right side. It's not as effective as the real pump, but it's better. It solves the problem. We use like rubber stoppers to seal the Buchner funnel to the vacuum flask. And sometimes one is not enough. See, this is like very loose. And when you're using the vacuum, air could go through this. And since it's not sealed, the filtration is not going to be very efficient. So we have to use more than one. We are using two here, one inside another, to make sure that it creates a better seal. So it's going to make the filtration more efficient, the vacuum filtration more efficient. Okay, need to measure the mass of filter paper. Okay, to measure the filter paper, I'm sure you have used scale balance many times already. You just press the tear button. It would tear. That makes it makes the weight 0. It is sensitive. So when it's teared, you place your filter paper and record the mass. Could you see the number, or you want me to read it to you? Why is moving so much? It's moving a lot. Okay, 0.1 0.180. Okay, 0.180. Yes, grams. You place the filter paper inside the Buchner funnel. You still have to add drops of water to make sure that it's is sealed, so the filter paper stays. If you don't add the water, the paper stays up, and as soon as you pour the mixture, some of the solid can go underneath, and we're trying to avoid all of that. Okay, to test the pH of the solution, you use a pH paper, and you test the solution. A red color is a good indication that this solution is acidic. The solution is acidic. It's been in ice for 5 minutes already. For recrystallization, for any of you who had organic 1 with me, is a 555 that I use. I say 5 minutes in icing. 5 minutes icing, that means you place this in ice bath for 5 minutes, your mixture or the mixture that is being crystallized or being precipitated, you place in ice for 5 minutes for complete precipitation to lower the temperature. Then you are going to vacuum it and run the vacuum for 5 extra minutes. Vacuum for 5 minutes. What's the purpose of vacuuming for 5 minutes? So it's going to make the drying step, which is the next step, faster. So how many times do I have to wash this? What should I use to wash the crystals? Okay. It's not as strong, but it's working at least. So for 5 minutes, we're going to wash it with cold water. Does the procedure says wash with acetone? Is that from procedure or prior knowledge?
Procedure says cold water.
Cold water, okay. Just use cold water. Step 9. Wash the precipitate with cold water and then place it in the oven for 5 minutes. So 5 minutes of the icing, 5 minutes vacuum filtration. It might sound like long, but you appreciate more because your sample is going to dry faster, especially this vacuum pumps. We are spoiled by using the central vacuum that is downstairs. It's a huge machine, and we are very careful not to destroy it, but right now it's really off. One time it was broken. It took like 6 months to fix it, but now it's just off because nobody's using it.
Professor, I have a quick question. Flask that's hovering there.
Vacuum flask.
Kind of flask?
Vacuum flask. One is vacuum flask here, and then
No, that one that you're pointing to, the one under the orange.
that is a trap. Trap is just a trap that if any water goes back, it's going to be trapped in there. So it doesn't go into the vacuum pump. It's like in between the vacuum pump and the vacuum flask. So we connect the vacuum flask to trap, and the trap is attached to the vacuum instead of directly attaching the flask to the vacuum. It's just to protect the machine. We use it for a longer time. Okay, the first 2 experiments are really long comparing to the others, and then you get like a couple of shorter experiments, then it changes. It's like but it's good. I used to, during the summer, at least for the 9 years, I was teaching the lecture, and most of the students I had them both in lecture and the lab. This summer, Dr. Chowdhury is teaching here the Organic 2 lecture for summer, and I teach the Organic 1 lecture. So we probably have extra time, but I use that time just to talk more about the actual what's happening in the experiment. So if you have any questions about the lab, I will be able to answer during the downtime of the experiment. Let me know if it's been 5 minutes or whenever it's 5 minutes for vacuum. I didn't keep track. I didn't mark. Yes. Okay. Has it been 5 or not yet? No? It's been 5 minutes or no? 1 more minute. Okay. Just want to make sure the oven is ready. Yes, it is. Good. Thank you. And bring the. Okay, we are going to use the Meltdown later on. I just brought it out to remind you if you have any questions about melting procedure. I'm sure you have used this organic one multiple times.
No, ma'am.
Questions?
I was saying no, I've never used that before. I have no clue what that is.
You haven't used melting point apparatus, like melting apparatus to measure?
No, ma'am.
No? Okay, I show you how to use it, no problem. Yes, this is the blue box. is not, it could be different shape or form in different campuses, but this is the Meltdown apparatus. It's called Meltdown, and the plate, the surface, you have switch on and off, you have a power regulator, and we have a chart that we can use that chart. We think we can have a chart, please. We use the chart to look at the chart and see what should we set the power regulator based on the chart, and I'm going to show you the chart. There is a thermometer holder slot, and then next to it there's something, thank you so much, and next there is something that is going to be capillary tube holder, a place for capillary tube holder. My Orgo 1 lab teacher did the same 3 labs over and over again, decrystallization, separation, distillation. Okay. Well, okay, very good. We got the mask for the filter paper, and now we need the mask for the product. But before we get the mask for product, I am supposed to let it dry for 5 minutes. This is the cake that you have, basically, and you can take it out just like cake, and you can flip it or slide it out of the pan or flip it, so you get your sample in and get as much possible of the crystals that is left. Place it on the filter paper, and I'm going to place in the oven. I come back with the Meltdown apparatus in case you have questions. I can help you with that. Okay, because the temperature is already at 100, you time it for 5 minutes, and it should be done. So with the Meltdown apparatus, we also have this. We have a room. I don't know if you've been. Some of you looks like you've been to here at Central Campus lab. Then we have an instrument room with like 10 or 12 of these machines there for each group to use their own machine. And this chart, it's basically saying if your compound has a melting point of between 100 and 150, the best setting here is going to be 4. If it's 150 to 200, it could be 5. If it's 200 to 250, it's going to be 6. This is like how fast you can heat the Meltdown apparatus. Now, what is wrong if you heat it too fast? Let's say your sample melts between 100 and 150. You place this setting at 8 because you've been in the lab for a long time. Then what's going to be a problem? The problem is for the sample to get, if you have a question for me, I'm really sorry if you had a question for me and I missed it because I hear the sound that chat is coming. And if I didn't answer, that means I didn't see your question. Please use the mic and ask your question. I don't mind at all. This is lab. It's supposed to be interactive. And for lecture, I didn't let the people use the mic until end of the lecture. But for the lab, anytime, please use your mic, ask the question. If I delay your answer, is there anything that I missed it, or I can go? go ahead and explain about this. Was there any question? No? Yes, yes, exactly. The exact range, yes. I'm going to continue then. So you would have to set this number according to your samples. In this case, your sample is unknown. Because your sample is unknown, we just look at the lowest possible melting point. The lowest possible melting point was 138. So I'm going to set this between 4 and 5. Now, if I set it at between 7 and 8, what's going to happen? The melting, the sample that is being melted is in the sample holder, which is attached to the oven for this machine. And with the oven gets really hot, and it gets hot really fast. Your thermometer, it needs time to show that temperature. So if you heat it up too fast, that means the machine is called meltdown. So if you heat it up too fast, then thermometer is going to lag the temperature. So basically it says thermometer is lagging the actual temperature. So the temperature that you are going to record is going to be, by mistake, by false, is going to be lower than the actual temperature that you have in the sample or in the oven. So this is like smooth and gentle heating. At the same time, if your sample is like, if it melts at 300 degrees Celsius, you don't want to put this at 2, because then it would take forever for it to dissolve, to melt. To prepare your sample, you are going to take a capillary tube. You should only touch the closed end of the capillary tube, never touch the open end of the capillary tube. If your sample is coarse, that means the crystal size are large, use Meltdown pastel to grind it well, and then you dip the open end of the sample into the capillary tube into your sample a few times. Then you are going to flip it, pass it through a hollow glass tube. When the sample dries, I'm going to show this one more time. I'll actually do it with you or while you're watching. Then the sample goes down. The size of the sample in capillary tube, it should be about 2 to 3 millimeter. It cannot be too high. What would be the problem if it's too high? If it's too high, then the top of the sample is going to be out of the range of your view. I'm going to hold this next to the camera, so you see this magnifying glass. There's like a round glass right there that you are going to look through that to see the sample is melting or not. So you should be able to see the sample. If you fill up the capillary tube like halfway, you place in there, you won't see it through that. You won't see the top of the sample. So when you have your sample, you turn on the meltdown and you wait, you monitor your sample until it's melted. When it's melting, initial melting actually is going to show on top of the sample. That's why it's important for you to see the top of the sample through that magnifying glass. So it's going to melt or sweat, and you see droplets of liquid on top of the sample. You record initial melting, and then you wait until the entire sample is melted, and you record final melting of the sample. If you leave your sample there and then you get distracted, you talk to your friends, and you go back and your sample is melted. Oh my God, I didn't record the number. What should I do? You take it out. It goes back to solid because it's cold. You cannot use this sample again, right? You cannot reuse a sample. If it's melted once. You toss this into a broken glass box. You get a new capillary. You prepare a new sample. Because if you heat up the sample, high temperature, especially, you don't know how much higher than the melting point the temperature went. Organic compounds, they decompose easily. So if you leave it in there, it's melted, past melting point, the chance that your sample was decomposed is high. And when you cool it down, you are not looking at same sample. This is a different sample. The other problem is the crystallization form, it can change. If the crystallization form changes, then you can get different melting point. A very good and obvious example of that is carbon in graphite form or diamond form. The melting point would be more than 1,000 degree difference in the melting point, and the reason for that is the crystallization form. So if the sample melts, it can go to different crystallization form, and this is just, it could. I'm not saying every time it happens, but it could crystallize in different shape of crystals, and then it's going to have different melting point. So you cannot reuse the same sample. You have to discard it and use a new sample. When it's 5 minutes, you let me know. We can try the melting point. And if it melts less than 100 degree, it means the sample is not dry. We have to do one more. But at least we can try it after the 5 minutes. Has it been 5 minutes? No?
Approximately.
Approximately. So I'm going to check. There is another way to check. For my eyes, are probably you, hopefully, you know, when you work in the lab, the filter paper, if the paper is dry and crisp, that means your sample is dry. So you don't have to really worry about extra water. Or take the melting point. If it's much lower than expected, that means it's not dry. If your sample is completely dry, the melting point is much lower, what's the conclusion? Conclusion is that your sample is contaminated. Washing was not efficient, so it's not pure. So let me check the sample. Not very good news. Your sample is not dry because the paper is soaked in water, because the vacuum that we use today is not the actual pump that we use, is that just the baby vacuum that we use. So we give like 2 more minutes and then try. Final mass of filter paper is not taken yet. Okay. I'm going to show you a trick how to, like, what I actually meant by talking to your sample. What I do when the paper still is too wet, I take another filter paper and I press it. I kind of absorb most of the moisture from the paper, and that makes the drying faster. So other things you could do, you take a smaller sample of your sample, you place them in a separate watch glass, because it's a small sample, it can dry faster. So when I said I was talking to your sample, that's what I actually meant. Okay. I took a small, very small sample of the actual sample. I let it dry on separate paper, and I'm going to measure the melting point. So first, I try to change this to powder form so it will fit into the capillary tube easier. Then I dip the capillary tube into the sample to make sure that it's getting inside the capillary tube. If it's dry, your work is much easier because it will go down faster, it will change to powder faster, and it will melt at the better temperature. So hopefully the sample is dry. And if it's unexpected result, you can actually, we have a chem wipe out or no? Okay, it's fine. It's better to wipe the outside of the capillary tube. Please, chem wipe would be nice. Outside of the capillary tube, because when you pass it through the glass tube, you don't want the glass inside the glass tube to be filled with the powder, because then the next sample, it might stick to the side. Thank you so much. Okay. If you hold the hollow glass tube straight, it would be better bouncing. So when I try to get the sample all the way down, I want to make sure that there is no air bubbles, air gap trapped here within the sample, because if there is an air bubble here, then air is not good conductor of the heat, and because it's not a good conductor of the heat, the heating of the sample is not going to be even. So two problems. Air is not a good conductor of the heat, it's going to insulate. The bottom portion would be heated up faster than the top portion, then you would have a wide range of melting, which by false, you could say your sample is not pure, because impure sample, they have very wide range of melting. And or you could just say that is uneven heating. The heating is not even distribution. So the heat is not distributed evenly. The sample is ready. Hopefully it's dry. I'm placing in the sample holder part of the melt temp and monitor it. We can monitor it together, but it might be blurry for you to see it. I'm not sure if you can. Can you see where the sample is by any chance? Or is hard? See where the sample is. Yes, okay. So that's where your sample is, and I'm waiting for the initial melting and the final melting, and I give those numbers to you. When you are doing two sample, you want to make sure your Meltdown apparatus is cooled in between, because if it's not cooled, then as soon as you put your sample in, so we are done with experiments, I can take my glasses off. As soon as we are it's blinking. As soon as we are done with the first sample, we should turn off the Meltdown, let it cool down. Because if it's hard, if it's hot, and you put your second sample, it melts right away, and you don't know what temperature was the melting. So the melting point, the temperature of the melt temp, it should be 10 degrees less than melting point of your new sample that you're going to put in. So to make sure that if you have an unknown, you have to do quick melt. A quick melt is like you take a sample and you melt it like very fast. You set it at high temperature and you get it melted. So if it melts at 150, then you wait until it goes down more than 10 degree, maybe like to 15, 20 degree lower. And then you get your sample again and try it again. For the, yes, the white is the white is hiding on the white. Yes, it's possible. What is that?
No, I was pointing out that the lack of contrast made it really hard to see.
Yes, it makes it. That's the multi-blurry is very hard to see. Even when you are in the lab, actually here, the only way you can see it is like if you move the capillary tube up and down. Otherwise, the background with the gray background that we have there, it's not easy to see it. Sometimes it's hard. So the melt temp, you let it cool, and while you're letting cool down, you should never take the thermometer out. Thermometer should stay in there, and the only way you want to take the thermometer if you just want to check that your thermometer is broken because you've been heating this for a long time and it's not moving up. The colored ink that is here or the alcohol is not moving up. So what you do, you check your thermometer. Like when you are at the doctor's office, the old ones, now the new ones, they just touch your forehead for your temperature. But they had these thermometers, or they use it for like kids. Sometimes we have to shake it. This is different from that. This is like the thermometer. You don't take it out, because if you take it out, it might sound funny, but when you take it out, you're measuring the temperature of the room. You're not measuring the melt temp to see how cold or how hot is the melt temp. So you should stay in, just wait, be patient until is melted. Okay, it's 100 and has not melted. That is good news. That means that your sample is dry, because if it was wet, it would have melted less than 100 degrees. So my son was complaining yesterday about staying home for too long. I bet it's the same for you guys. The chlorotoluene unknown is unknown B, and you need to.
It was the chlorotoluene, correct?
No, is the final product. Chlorotoluene is liquid. When you oxidize it, it changes to chlorobenzoic acid, and the final product was the crystals, the white crystals. That's what is what's in the meltdown now. We are measuring the melting point for the final product. The melting point, I'm still waiting. And the beta of the sample also we are still waiting, because I took a very tiny sample of the
Oh, so it won't affect the ending mass?
Yes. So we don't have the mass yet. So I'm going to return what I have in the capillary tube and on this filter paper to the original one to add it up for the mass. But I'm giving time for it to dry up. Add bad lab technique. Okay. It's at 1:32 and has not melted yet. Kind of. So do you have any questions? Any questions for me?
I'm good so far, Professor.
That's good.
Good opportunity to work on Experiment 13's lab notebook, though.
Oh, that works. That works, especially next week. Since we already talked about assembly for reflux, you already know, so I'm going to probably assemble it faster. And then we talk about the experiment, then you have some time, you can work on something else. But you don't have lab this Friday. Your Friday lab starts next week. So your next lab would be next Tuesday. I think this Sunday you have one lab report though for this experiment.
In a perfect world, the goal is, before Orgo lecture gets insane, because it will, is to do like a whole week's worth of lab notebooks ahead of time.
That's
We'll see
great.
if that happens.
Yes, that's good planning. That is good planning. You mean this class is that lecture or the lab?
If organic chemistry, I am afraid of it. I am not very good at this subject. I'm
Who
really bad at it.
Who really made you be afraid of organic chemistry? Organic chemistry is the better chemistry.
Oh, it's not that anyone made me afraid of it. It's the C that I was ever so fortunate to barely scrape in Orgo 1.
Oh. Orgo 1, I don't know. I really don't know. I always, when I start teaching organic lecture, I did teach lecture for, I think I told your class that I was teaching lecture for,
I mean, perhaps it's just the fact that it's a class where you should be writing everything out, but due to what's going on in the world right now, we have to do multiple choice exams on our lecture class, and that
really?
makes the tests just so ungodly difficult, because if you don't know everything, you can't like go for partial credit by writing what you know out. It's just wrong.
So why multiple choice? Your exams here are not multiple choice.
In Professor Chowdhury's class, they kind of have to be multiple choice because that's just the way she has to write the exams now. The first exam was all long answer, and I loved that exam.
Wow. I didn't know it has to be multiple choice. I'm planning to give free response to my organic one class. Actually, it's not all free response. I have like 50-50.
It's just hard to do like mechanisms and stuff because we can't draw it out.
Okay, I see. Yes, that's right.
I'm used to blue books up at Columbia, and like that was kind of how I learned to take tests. Multiple choice is weird.
Yeah.
It's also easier though because if you know the reagents, all you have to know is the product, so it makes it easier that way too though.
I'm going to just for like 30 seconds. I just want to check one thing. here, if you don't mind. I'll be right back. I'm checking something about this unknown. Can you do me a favor and turn off the oven, please? Thank you. Wow. Okay, it's 210 and sample has not melted yet. So mass for filter paper and product. Mass for filter paper and product is 0.687. 0.687. Yes. Okay, initial melting 230.
Is the 0.687 just the mass of the product already subtracted from the filter?
No, the percent yield was not too high. Okay, the sample is melted at the 233. So initial was 230 and the final is 233. And you got the mass for the product plus the filter paper was a 0.1 something was the paper. So you need to subtract that. I did not record it. I should have, but I didn't record it. So it should be in your papers now.
Yes, if you scroll up far enough, we've posted all of the figures that you've shared with us, Professor.
Okay, perfect. Okay. That's the last step of the experiment today. Do you have any questions for me? I'm going to stop the recording and give you some time to do data analysis. You need some time to do data analysis. You need to some time to write your report. So it's not that we are ending the lab, but we are done with the actual experiment.